Hey, today we're going to talk about a technique called implicit differentiation. Let's start with an example. Suppose you have the equation x times y equals 1, and we want to find dy dx, the derivative of y with respect to x. Well, one way we could do it is we could do a little algebra, solve for y, and get y equals 1 over x. And we've taken this derivative before a handful of different ways. We would eventually get that dy dx is negative 1 over x squared. But I don't want to do that. I want to try something different. I want to start with the equation x times y equals 1 and simply take the derivative of both sides of that equation as it stands. In other words, if x times y is equal to 1, if they're the same thing like they are, then the derivative of x times y has to be the same thing as the derivative of 1. And how do you take the derivative of x times y? Well, it's a product, so we need the product rule. And the product rule says it's the derivative of the first, and the first is x, and the derivative of x is just 1, times the second, so that's times y, plus the first, which is x, times the derivative of the second. And what's the derivative of y? Well, it's the derivative of y, dy dx. And what's that equal to? It's equal to the derivative of 1, which is 0. And now we can solve this equation for dy dx. We subtract y from both sides, and then divide both sides by x to get that dy dx is negative y over x. And you say to yourself, how come that doesn't look like the answer we got above, where dy dx was negative 1 over x squared? And it's because, well, y is 1 over x, so negative y over x is negative 1 over x, which is just negative 1 over x squared, like we saw before. And this technique of taking the derivative of both sides of an equation that has maybe mixed x's and y's together is what's called implicit differentiation. Let's do another example. We'll use implicit differentiation to find the slope of the line tangent to x squared plus y squared equals 1 at the point 1/2 square root of 3 over 2. Now, x squared plus y squared equals 1 should look familiar to you. That's the equation of the circle centered at the origin of radius 1. In other words, the unit circle. And 1/2 square root of 3 over 2 is certainly on that circle. If you plug in 1/2 for x, 1/2 squared is 1/4. Square root of 3 over 2 for y, square root of 3 over 2 squared is 3/4, and 1/4 plus 3/4 is 1. So this point is on the unit circle. And before we actually do this problem, it's worth recognizing that the curve that we're talking about, not even a function. It's a circle. It fails the vertical line test almost everywhere. And so here we are, and yet it certainly has a tangent line at any point on the circle. That's where tangent lines came from, circles. You know, a circle has a tangent at every point. And so here we are about to do calculus on some curve that is not even a function. So that's pretty cool. And this is the basic idea behind implicit differentiation. We simply take the derivative of both sides of the equation with respect to the variable x. We will often leave out writing this step and just start right in taking the derivative, but keep in mind that that's what's going on. We are taking the derivative of both sides of the equation with respect to the variable x. And on the left, the derivative of x squared is obviously just 2x, but the derivative of y squared is more complicated than that because y is not the variable, x is the variable. Y is some function of the variable. And so in order to take the derivative of y squared, we need the chain rule. You treat the y as if it were a variable, and if it were a variable, then its derivative would just be 2y. And then you finish by multiplying by the derivative of this function that we just treated like a variable. And the function that we treated like a variable was y, and its derivative is the derivative of y, dy dx. And this is all equal to the derivative of 1, which is 0. All that's left is to solve for dy dx. And when you're through doing that, you get that dy dx is negative x over y. And this is very common in these kinds of problems, that your answer will be some mixed expression including x's and y's. But we haven't actually answered the question yet. This gives us the derivative dy dx of this curve, but we're trying to find the slope of the tangent line at a particular point, and it's the point where x is equal to 1/2 and y is equal to the square root of 3/2, and so all that's left is to plug in those values. And we plug in those values, x is 1/2 and y is the square root of 3/2, and we do some simplifying. Dividing by the square root of 3/2 is multiplying by 2 over the square root of 3. And then we come up with an expression, -1 over the square root of 3, and it's polite to rationalize the denominator, and in the end you get -square root of 3/3. Okay, I'll do one more, and then it will be your turn. We take the derivative of both sides, and starting on the left, the derivative of 5y squared is a chain rule problem because the variable is x, not y. Y is some function of the variable. And so how do you do it? Well, you treat the y as if it were the variable, and that gives us 10y. And then you have to multiply by the derivative of the function that you just treated like a variable. And the function we treated like a variable was y, and so its derivative is dy dx, the derivative of y. And now we're ready to move on to the derivative of the sine of y, and it's the same thing. If y were the variable, the derivative would simply be cosine of y, but it's not. X is the variable and y is a function, and so we treat that function as if it were the variable, and that part gives us cosine of y, and then we have to finish by multiplying that by the derivative of the function we just treated like a variable, which again is dy dx, the derivative of y. And this is all equal to the derivative of x squared, which is 2x. All that's left is some algebra. We need to figure out what dy dx is equal to. So what we do is get everything with a dy dx on one side of the equal sign, and everything that doesn't have a dy dx on the other side of the equal sign. Well, we already have that in this particular case. And then we can factor out a dy dx on the left. That gives us this expression here. And now we're in great shape. All we have to do is divide both sides by 10y plus the cosine of y. And that gives us that dy dx is 2x all over 10y plus the cosine of y. Okay, your turn. Start with this one. Take a moment, see if you can figure this out by implicit differentiation, find dy dx. So pause the video, and when you're ready, start it back up. Taking the derivative of both sides, well, the derivative of 2x is just 2. The derivative of 3y is 3 times the derivative of y, and the derivative of y is just dy dx. And the derivative of 7 is equal to 0. And when you solve that for dy dx, you get that dy dx is equal to -2/3, and you say to yourself, I wonder why I got an answer that doesn't have any variables in it. And it's because 2x plus 3y equals 7 is the equation of a line. And in particular, it's the equation of a line with a slope of -2/3. And so the derivative, which tells you the slope of a tangent line anywhere, is -2/3 for any values of x and y. Okay, try this one. Far more interesting. So take a few minutes. See if you can work this out. Find dy dx using implicit differentiation. Pause the video. When you're ready, start it back up. On the left, the derivative of x cubed is 3x squared. For the derivative of y cubed, we need the chain rule. You treat the y as if it were a variable, and that gives you 3y squared. And then you have to multiply by the derivative of the function that you just treated like a variable. That function was the function y. Its derivative is dy dx. On the right, we have a product, and so you have no choice. You have to use the product rule. And the first function is x, and so the derivative of the first is 1. Derivative of x is 1 times the second, so that's where the 1y comes from, plus the first function, x, times the derivative of the second. And the derivative of the function y is dy dx, the derivative of the function y. All that's left is algebra. We want to solve for dy dx. So we get everything with a dy dx in it on one side of the equal sign and everything that doesn't have a dy dx in it on the other side of the equal sign. Meaning subtract x dy dx from both sides of the equation, and subtract 3x squared from both sides of the equation. Then everything on the left side of the equal sign has a dy dx, and everything on the right side of the equal sign does not. That lets us factor out a dy dx on the left-hand side of the equal sign, and then we can divide both sides by 3y squared minus x to get this answer. Dy dx is y minus 3x squared all over 3y squared minus x. Okay, let's do one more just for fun. We'll find the equation of the line tangent to the curve cosine x plus cosine y equals 1 at the point pi over 3 pi over 3. So first of all, you should convince yourself that that point really is on this curve. If you plug in x and y both equal to pi over 3, well, cosine pi over 3 is a half, so this is a half plus a half is equal to 1. And so that point, pi over 3, does satisfy this equation, and so it is on the curve. And if you take a moment to try to picture in your mind what the graph of cosine x plus cosine y equals 1 looks like, then I'm sure you all imagined something like this. Yes, this is what the graph looks like, and it's even crazier than it seems at first. It goes on in every direction like this, up, down, left, and right. It just keeps on going forever, these crazy little misshapen bubbles. So this is part of what's so beautiful about implicit curves, is that you get some very strange graphs that we are doing calculus on. We're computing the equation of a tangent line to one of these crazy little bubble-shaped things. Getting back to business, there is some calculus to be done. We take the derivative of both sides of the equation cosine x plus cosine y equals 1, and the derivative of the cosine of x is the negative sine of x, and the derivative of the cosine of y is the negative sine of y times dy dx by the chain rule. And the derivative of 1 is equal to 0. And after you do a little algebra to solve for dy dx, we get that dy dx is negative sine of x over sine of y. And at the point pi over 3, that gives us that dy dx is the negative sine of pi over 3 divided by the sine of pi over 3, which is negative square root of 3 over 2 divided by square root of 3 over 2, or just negative 1. And so we have that the tangent line is y equals negative 1x, or just negative x plus b. And all that's left is to plug in x and y to solve for b, which yields b equal to 2 pi over 3. And so the tangent line at the point pi over 3 has the equation y equals negative x plus 2 pi over 3. And there are lots of other cool curves for which you can use implicit differentiation to find the derivative. And I'm sure it won't surprise you to hear that I've prepared a fine homework assignment for you to practice on. So please do. Don't forget, as usual, to have fun doing it. And I will see you soon. Bye.